Okay, so Chapter 2 is about how we're going to organize and summarize data. And so Chapter 1 was a lot of vocabulary and how to collect data. And now Chapter 2 is, now that we have the data, what do we do with it? And really a good rule of thumb is when you're collecting data, you want a large amount of data. And the problem is well, it's kind of a double-edged sword. The more data you get, the better, but the more data you get, the more numbers that you have to deal with. And let's say you have 1,000 numbers and you just see all those numbers. That's a lot of numbers. Who knows what it means? So that's why we organize and summarize, and we're going to learn how to do that. So 2.1 is organizing qualitative data. Remember that qualitative is a category data. What's your favorite starburst? What's your hair color? That's the type of data that we're going to look at in 2.1, and there's certain ways to organize that type of data. We're going to look at how to organize them with using tables, bar graphs, and pie charts. When data are collected from a survey or designed experiment, they must be organized into a manageable form. Data that is not organized is referred to as raw data. So that's basically, you've got just rows of numbers, lots of numbers, and it's just a little probably overwhelming at first if you've got all those numbers and it's not organized. And so we want to take that raw data and organize it into one of these three ways: tables, graphs, or numerical studies, which we won't see until Chapter 3. So a frequency distribution lists each category of data and then the number of occurrences for each category of data. So it looks like this. It's your category, whatever that may be, whether that be starbursts and you put, I've got a red starburst, I've got a pink starburst, whatever that may be. And then this middle column is really up to you if you want to use it or not, but it helps people organize, and I call it the tally column, and you tally how many red starbursts exist. Maybe you count 3, and then you count 5 pinks in our raw data. And then the last column is where the frequency goes. And I'm going to abbreviate that with FREQ. But really, frequency is abbreviated with a little fancy F. And that means frequency. And the frequency is that numerical value. So I'd put 3 for red and 5 for pink. That's just an example. We'll look at a more specific one in a second. Okay, so it says the data below shows colors of M&Ms in one randomly selected bag. Construct a frequency distribution for the color of plain M&Ms. So we're going to do this on the next slide, but just remember this is where I'm getting my data. So if you want to take a picture of it so you see where I'm getting my numbers. But basically I'm going to go down the line, I'm going to count. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 browns. So that's where I'm going to get my number, and I'm going to do that for every single one of them. So bear with me, but I will be using this in a second. And then we are going to do something else called a relative frequency. It basically creates a proportion for the frequency that you're given divided by your total number. So it will always be in the form of a fraction, decimal, or a percent. That's what a proportion is. And it should always add up to 1. But I'll kind of show you how we do that in a second too. But that is called a relative frequency distribution. And you're always going to use this formula. Whatever the frequency was divided by your total amount of frequencies. So it says use the frequency distribution, which we haven't done yet, we're about to do, and make a relative frequency distribution of the M&M data that we looked at. So What am I talking about? M&M colors. I'm just going to put M&M C for colors. And then if you want, you can do a little tally. And then frequency. And then relative frequency. So what colors did I have? I had brown, yellow, orange, blue, and green. And you can, again, this tally column is optional, but let's say I went through and I tallied all the browns and I got 12. And then the yellows I got 10. The reds I got 9. Orange 6. Blue 3. And green 5. So that's when you actually put the numerical value for the frequency. So 12, 10, 9, 6, 3, 5. Then the relative frequency is part out of whole. So what's our whole? What do our numbers add up to? 45. That's our total, or our whole. And so to get that part over whole, we're going to do 12 divided by 45. And I get 0.2667. I always go to 4 decimal places. If you want to represent that as a percentage, you just need to move that decimal. I'm going to do this up here just because I'm running out of room. 2 places to the right. That is the same as 26.67%. I'm going to represent all of these as decimals, though, just because I don't have the room. So yellow is 10 out of 45, which is 0.2222. Red's 9 out of 45, which is 0.2. Orange is 6 out of 45, 0.1333. Blue's 3 out of 45, 0.0667. And then 5 out of 45, which is 0.1111. If you add all these together, it should get you really close to 1. If you get, say, 0.1001 or 0.999, that's okay because that's just because of rounding. But you should get close to 1. That tells you that you did it correctly. If you add these up and get maybe 0.5, that means you only took into consideration 50% of your value. So just be careful, and that's really a way to just check it to make sure you got all the values. So we know how to do frequency and relative frequency distributions, and so now we can put that data in a graph. And a bar graph is what we're going to talk about right now. It's constructed by labeling each category of data on either the horizontal or vertical. We'll use more horizontal with the category. And then the frequency or relative frequency on the other axis, in our case, the vertical. Rectangles of equal width are drawn. The height of each rectangle represents the category or frequency. And what you need to know about bar graphs is the bars do not touch. Bar graph bars do not touch. Okay, so we are going to use the M&M data to construct a relative frequency bar graph and a frequency and a relative frequency bar graph. So I'm going to do relative frequency first because I don't have enough room. Then I'm going to have to erase it and go from there. So let's see. I'm going to go like this. And I'm going to write in black because it's a little smaller. So I'm going to label. So the color of my M&Ms go here. my frequency goes here, and I'm going to go off of that chart that we made earlier. So I've got brown, yellow, red, orange, blue, and green. Try to evenly distribute them, that they're spread out an even amount. Try your best. And then our highest number was 12. So our highest frequencies was 12. So I'm going to make 12 little tick marks if I can. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12. And I'm only going to write every other number just because of space. So 2, 4, 6, 8, 10, and 12. And then I'm going to make a bar for each one. So brown had 12. So I'm going to go up to 12. Create a bar. And remember, these don't touch. So yellow had 10. So I'm going to go to the 10 mark and not touch the brown. Go from there. Let's see. Red had 9. Orange had 6. Try your best once again. May not be perfect, but as long as it's pretty close. Blue had 3 and green had 5. And so that's our bar graph for our frequency data. And we are going to make one for our relative frequency. The only thing that's going to change is that we're using relative frequency on that vertical. So, yuck, that was not a straight line. Try a little better. That still wasn't great. Sorry. So we've got color. And so we've got brown, yellow, blue. Nope, that's red. Sorry. Red, orange, blue, green. And this time we're using that relative frequency, and the highest one went up to 0.2667. So I'm going to count by 0.05. So we can make a little more room here. So let's see. 05, 10, 15, 20. Whoops, it's not very spread out. 25, 30. Okay, so let's see. Brown was 0.266. This is the same thing, just new numbers on that vertical axis. The numbers are not going to touch. Yellow was 0.2222. Red was 0.2 exactly. It's nice. Orange was 0.133. Blue was 0.06. And green was 0.111. So you can see that although the numbers on the vertical axis are different, and I need to label this, M&M data. Although the numbers are different, it still creates the same shape because it's relative to the frequency. Okay, a Pareto chart is a bar graph where the bars are drawn in decreasing order or relative frequency. And so really with decreasing order, it's going to go just down. You're going to have bars and they're going to be just decreasing, 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 the biggest to the smallest. So if we constructed a Pareto chart for the M&M data, if you go back to the bar chart slide, it looked like this. It pretty much was already in order. but then it went, what did it do? Basically, this last one was out of order. And so if we were to switch our blue and our green, switch these two last ones, it would be in order. So that's pretty much what we're going to do. And anytime you need to construct it, just look at the frequency and put it in highest to lowest. So same thing. Here's our color. I'm going to do frequency, although it still works with relative frequency. And brown was the highest at 12. Then yellow at 10, then red at 9, orange at 6. Now, normally we had blue, then green, but green had 5, so we're going to do that first, and then blue because it had the smallest amount. And I'm going to count by ones again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then only put a number for every other one just for room. And do the same thing. So brown had 12. Yellow had 10. Red had 9. Orange had, what did orange have? 6. Green had 5. And blue had 3. So literally we just switched those last two, that green and that blue, and now it's considered a Pareto chart. It all is descending. It's decreasing. So you don't have to do this unless it specifically asks you to do a Pareto. In any other case, I usually just do the ones that I see first. So I saw brown first in the raw data, then yellow. But anyways. Okay, there's also something called a side-by-side bar graph. And that is when maybe you want to compare data. You can literally put it side by side and it really helps you compare. But let's say we want to know whether more people are finishing college today than in 1990. We could draw a side-by-side bar graph to compare the data for these two different years. The data set should be compared by using relative frequencies because different sample or population sizes making comparison using frequencies are difficult or misleading. And I'll kind of go a little more into that in a second. Okay, so example 5 says the following data represent the marital status in millions of U.S. residents 18 years of age and older in 1990 and 2006. Draw a side-by-side relative frequency bar graph of the data. So we've got 1990, 2006, and we've got 4 categories for each year: never married, married, widowed, and divorced. And remember, to find relative frequency, I need to add all these together. 181.9 to get my total. And for example, for never married, I would do 40.4 divided by 181.9, and I get 0.2221. And so that's the number that I'm going to put there. And I'm going to put numbers for each one of them, and that's how I'm going to get those numbers. And then 2006 is going to have a different total. That total is going to be, 219.7. And I'm going to do the same thing for the 2006, but I'm going to divide them by 219.7. And so the numbers that I'm about to put next to each of those are the relative frequencies. So 0.2221, 0.6190, 0.07, don't want that to go away. I'll write that again. 0.2221, 6190, 0759, and 0.0830. Then I'm going to do the same for 2006. I get 0.2517, 0.5812, 0.0633, and 0.10. 1083. And I'm going to make a side-by-side bar graph, and I'm going to try my best with the space that I have, but so we're going to put the status, which I'm sorry if that's going to be hard to see. I'm going to put NW for never married, married, widowed, divorced. And then the frequency is going to go, I'm going to draw a little arrow because I don't have enough room. Relative frequency is going to go vertically. And the highest I see is 0.6190. So that's kind of what I'm going to use to see how high I'm going to go. And I'm going to go, let's see, I'm going to count by 0.1. So 0.1, 2, 0.3. Whoa, I got really off really fast. Let's see, 0.3, 4, 5, actually. Sorry about that. 0.4, 5, 6. It's a little hard to navigate sometimes. Okay, so in a side-by-side, our bars can touch when you're comparing the years. So, for example, and I'm going to do a little key over here. 1990 is going to be black bars, and 2006 is going to be my green bars. And if you don't have a different color, you can just like make a little pattern in one of them, or shade one of them. Either or works. So anyways, 1990 for never married was 0.221. For married was 0.61. That I'm going to get up here in that one. Try to make your bars straight. As you can see, it's a little difficult for me. Widowed was 0.07. And divorce was 0.08, which I know those are kind of hard to draw. I should actually make them a little shorter. But try your best. And then I'm going to do 2006, and I'm going to do that in green. And so never married was 0.25, 0.58, widowed a little less. Let's see. And divorce was 0.10. So, a couple things. I know that right now this looks way bigger than 0.1083, but it's kind of hard when these numbers are so small. But the main thing is we knew that divorced for 1990 was much less than 2006, so you definitely need to represent that when you're drawing those bars next to each other. We can see and we can compare these years a lot easier now that they're organized this way. We know that in both years that married was the highest. But if you look, the reason we do relative frequency is because 1990 looked like less people were married than 2006, and that's just because there are more people who are living now in 2006 than 1990. But when you do a relative frequency, 1990 actually had more, which means proportionally in 1990 more people were married. And so that's why we do relative frequency versus frequency when we compare things that may have a different data set, meaning 1990 definitely had less people than 2006. All right, so this next one is just so you know it exists, a horizontal bar graph. The bars may also be drawn with horizontal bars, and they're made preferable when category names are lengthy. So this is an example of a horizontal bar graph. So it's literally like we flipped it. And so here's our categories, and then here on the horizontal axis is where our relative frequency or frequency would go. And this is just what it looks like. And again, it's kind of, you use it when your categories are lengthy and you don't want to draw them on the horizontal axis. And this is a side-by-side horizontal bar graph because the bars are horizontal. All right, one of the last things that we're going to talk about in 2.1 are pie charts. You may have heard of pie charts before, but it is a circle. It looks like a pie, and it's divided into sectors. That's the area, basically, of each portion of that pie. And each sector represents the category of data. The area of each sector is proportional to the frequency of the category. And so we're going to look at that really quick. An example. Okay, so example 6 is constructing a pie chart. And like I said, it's just a circle, and we need to represent pie charts with well, it doesn't matter. I like to do it with the percentage, but you can do it in decimals if you want, but I'm going to do mine in a percentage. And it says the following data represents the marital status in millions of U.S. residents 18 years of age or older in 2006. And so whenever we do this, we do want it basically in relative frequency, and right now it's in frequency. But this is the data we were given earlier, so I'm just going to go ahead and write that information down again. Never married is 0.2517. Married was 0.5812. Let's see, divorce was 0.0633. And, oh wait, that was widowed, I'm sorry, and divorce was 0.1083. And so right now, these are in decimal form, and if you want to use decimal form, that's completely fine. I'm going to change it as a percentage, and I'm going to make another little chart over here that represents percentages. If you want to represent it as a percentage, you need to move that decimal place 2 times to the right, or you can multiply by 100 in your calculator, and it will give you something that represents it as a percentage. So anyways, this is 25.17%. 58.12%, 6.33%, and 10.83%. So when you do the pie chart, it looks like a pie. It's a circle. Try your best. Not too bad. And I always start with the biggest. So married is 58, which is kind of easy because that's a little more than half. So I'm going to represent that with an M for married. Never married is next with 25.17, which is about a quarter. And then widowed and divorced is left over. Divorced is almost half of widowed. That looks more like exactly half. Let's do this. Okay. I'm going to draw a little tick mark to this because I don't have enough room. This one's bigger. It's divorced. And that one's widowed. And if you want, you can put the percentages. I'm just going to round, so that would be 58, 25, and so on. For each one. 6. And I guess I could put 11 for this one. So anyways, that's how you construct a pie chart. Okay, so 2.1 was all about organizing qualitative data, and 2.2 is all about organizing quantitative data. So here's what we're going to do. We're going to organize discrete data, construct histograms of discrete data, organize continuous data, and histograms of continuous data. Then we're going to learn how to do a stem and leaf and a dot plot. And then we're going to talk about shapes of what graphs could produce, the different shapes. So the first thing is whenever you summarize quantitative data, you need to first determine if it's discrete or continuous. And remember, discrete is counting numbers like the number of siblings you have, and continuous is infinite, like speed. It can be very, very, very specific. So if it is discrete, there are very few values, and the categories of data will be observations. So we'll kind of go into this a little more, but most of the time when it's discrete, you're going to have single value classes. And if it's continuous or if it's discrete, but there are lots of different values, then you do something called interval value classes, which basically groups the numbers. But again, we'll kind of talk about that as we go along. The following data represents the number of available cars in a household based on a random sample of 50 households. Construct a frequency and relative frequency distribution. So for quantitative data, you can still do the same thing as far as frequency and relative frequency distribution goes. And so we know that our sample size is 50, so we know our number should add up to 50 as far as frequency goes. And so let's see, what are we talking about? Number of cars per household. And then I'm going to do frequency and relative frequency. So the different types of cars, we've got 0, 1, 2, 3, 4, and 5. If I were to count up all the zeros, 1, 2, 3, 4. So the frequency there is 4, and so that's how I'm getting these numbers. There are 13 ones, 22 twos, 7 threes, 3 fours, and 1 household that has 5 cars. And just to check, I know I should get 50, but go ahead and add up what you got, because let's say you add this all up and you get 49, you know you missed a value, and you need to go back and figure out where you missed it, because it'll mess up the rest of your data if you do. And then to get relative frequency, I'm going to divide each of them by 50. So 4 divided by 50 is 0.08. 13 divided by 50 is 0.26. 22 divided by 50 is 0.44. 7 divided by 50 is 0.14. And so on, 0.06, 0.02. So that's our information. And if we add all these up, we should get 1. That's a whole. And so that lets us know that we did it correctly. This has a histogram constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of the class. The width of each rectangle is the same, and the rectangles touch each other. So histograms, basically the difference between histograms and bar graphs are the rectangles touch each other, and histograms we use for quantitative data, and bar graphs we use for qualitative data. And I'm going to go ahead and create a histogram based on the data that we just found. It tells us to do that on the next slide, but there's really not enough room there. And so I'm going to go ahead and do that. So let's see. We had talking about cars. 0, 1, 2, 3, 4, and 5. And the frequency went up to 22. So I'm going to go ahead and count by 5s. And you need to make sure that you're labeling that it's a frequency distribution. And so for 0, we had 4. And I usually do it right in between the one I'm doing and the next one so that they're evenly spread out. 1, we had 13. 2, we had 22. 3 was 7. 4 was 3. And 5 was 1. And so, again, the bars are touching. Now, I'm going to see if I can manipulate this without having to draw the whole thing again. and do my relative frequency. So let's see, we've got relative frequency. That went up to 0.2, no, that went up to 0.44. I'm going to count by tens. 1, 2, 3, 4, 5. So 0 is 0.08, that's about right. 1 was 0.26. I'm going to make that a little shorter. 2 was 0.44, that's about right. 3 was 0.14. Should probably be a little smaller. 4 was 0.06. Make that a little smaller. And then I'll leave 5. That was about the same. Whoops. And then 5 was about 0.02. But anyways, the only thing that's going to change are these numbers on the side. The shape should stay the same, so we're going to leave that. And this was the slide that said to draw it, and this is where we got the data that we drew that information from. So I did that on the previous slide, so I'm going to go ahead and move on. This says organizing continuous data. So whenever we organize continuous data, we are, let me tell you what we're looking at first. The following data represents the number of persons aged 25 to 64 who are currently work disabled. And so there's a lot of information here. We're talking about thousands of people. And so whenever we have something like that, we want to try to group them. So there's a group, 25 to 34, and in that there were 2,132,000 people that are disabled between that age limit. And so this 25, 35, 45, 55, that's called the lower class limit. It's the smallest value within each class. The upper class limit is 34, 44, 54. That's called the upper class limit. And then it says the lower class limit of the second class is 35. The upper class is 34. The reason you do this is because you don't want to say 25 to 35 and then 35 to 45, because then you're going to have two values that could fit in each category. And so you kind of have to be careful about that. But anyways, this is kind of another way to organize data that can make it a little more pleasing to the eye, because if we didn't, we'd have a lot of different ages that we would need to look at. Lastly, the class width can be found by finding the difference, aka subtracting the lower class limit. So we could have subtracted 35 minus 25 to get 10, 55 minus 45, it doesn't matter, but that width is 10. Okay, so this says the following data represents the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. Construct a frequency and relative frequency distribution of the data using class widths of 10. So basically, all of this is our raw data. And it's just not easy to see right now. There's a lot going on. It's hard to kind of summarize this data. And so because the numbers are so big also, we're going to go ahead and group them. And I actually have already grouped them for you, but I'm going to kind of show you what's going on. And so if it said class widths of 10, the first thing you need to find is your min and your max. And so my minimum value, basically so you know where to start, my min value is 672. That is the smallest value. And my max value is 738. And so class widths of 10 is just like the one we saw earlier where we're jumping by 10 each time. And I really don't want to start at 672 because that means that the next one's going to be 682. It would just be kind of annoying. So I'm going to start at 670, given that information. And I'll kind of show you what that would look like. And so 670, 680, 690, 700, so on, so on, so on. And how you create the group is, what's the number right before 680? 679. Sorry. What's the number right before 690? 689, 99, so on, so on, so on, until you get all of those numbers that are included. And then you say, okay, how many numbers are actually between 670 and 679? So I'm going to go down. Well, I already know that wherever it was, 670, 679. There's one. Thought there was another one. Oh, there it is. So there's two values. So I'm going to write over this. There's two values that lie in that interval. And you would just keep going. There's 0 that lie between 680 and 689. And then you'd say, okay, I'm going to count, and there's 7 that lie between 690 and 699. And so on, so on, so on, until you get all your values, which are 45. I'm going to show you another chart in a second, though, because this is hard to do with this chart on there. This says you can also organize it by changing the width. So really, there are some good ways in choosing how wide you want to go. So, for example, ours were just now 10, but I'm going to show you one with 5 with the exact same data that we just looked at. And it honestly, it doesn't mean that one's better than the other. And most of the time, if you were given this question on quizzes or tests, I'll give you the class size. But here's what it would look like if you split it up into class widths of 5. So we're counting by 5. 70, 75, 80, 85, so on, so on, so on. And then you go in with that data and you say, okay, I see one that's between 670 and 674. One that's between 75 and 79. All of this, that means that there were no values here, no data that represents between, let's see, what is that, 680 and 694. And if that's the case, then you just don't have any. And so as you can see, it kind of organizes it for you. Here's technically the mathematical way of finding the class width. I'm not sure why. Whoops. That is messing up. I apologize. I'll tell you what it says. So you always need to find the smallest observation and the largest observation. And you need to figure out kind of how the range of your class size, your class size, the range of your data, and determine how many classes you want. That determines how big they need to be. And again, this can kind of vary a lot. So that's kind of why I do it for you most of the time. But if you really want to do it, you can do the largest value minus smallest value divided by the classes, and that will give you the class width. And this statement down here that's kind of cut off says, round this value up. Always round up whatever you're given for class width. Okay, so this says construct a histogram for continuous data. So we're going to use that eruption time that we kind of started grouping in class sizes of 10. And I'll just tell you the frequency for each. So frequency, and I do not have enough room to write all this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. But I will write the first one so you can kind of see where I'm getting at. This first one was 670 to 679. Sorry, see, I don't really have enough room. This one's 680 to 689, 690, 699, 700, 709, 710 to 719, 720 to 729, and 730 to 739. Remember, these were those groups, and we went in and we said, okay, how many were between 670 and 679, and we got 2. Well, if you were to add them, if you were to go through each one of these groups, the highest frequency was 11. So I'm going to count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And count by twos. 2, 4, 6, 8, 10. Okay. So this is a histogram, which means the bars are going to touch. So from 670 to 679, we had 2 observations. 680 to 689, we had 0, so we're literally not going to draw anything. 690 to 699, we had 7. 700 to 709, we had 9. We had 9 from 710 to 719. 720 to 729, we had 11. That was our most frequent observation. And then 730 to 739, we had 7. Sorry, my bars are a little lopsided. But that's what that histogram would look like if you were to construct it with continuous data. It's the same thing, but you just kind of group that data together. Okay, so stem and leaf plots are the next thing that we're going to talk about, and they're fairly straightforward. So there's some steps, if you will, that you want to use. And it says to identify the smallest place value given, that will be the leaves. And a stem and leaf looks like this. You put part of it over here and part of it on the other side. So the smallest value goes to the leaves and the largest value goes to the stems. And then you want to arrange them from least to greatest. Draw a vertical line to the right of the stem, so that's what that is. And you want to rearrange them in ascending order, so I'll show you what I mean by that. Okay, so this says draw a stem and leaf plot. An individual is considered to be unemployed if they do not have a job but are actively seeking employment. The following data represents the unemployment rate in each of the 50 United States plus the District of Columbia in June 2008. So here's all the states, and here's the data that we're given, the unemployment rate. And so for each one of these, I'm going to kind of start writing this, but I'll erase it and go with it later. So, for example, Alabama, let's just talk about it, what it would look like for a stem and leaf real quick. It would be 4.7. So that whole number goes in the stem, and then that tenths place goes as the leaf. So that reads 4.7. I'm going to do that again. And then the goal is, really, you want to find your smallest value, which is 2.8. I already had that written down, but now I can't find it. Oh, here it is, South Dakota. So we start with the smallest value. Stem, leaf, I have 2.8. All right, great. But then you keep going. So I don't have any more 2s, so I'm going to move on to the 3s. And I've got Louisiana 3.8. North Dakota 3.2, Nebraska 3.3. So these are all reading 3 different numbers, right? 3.8, 3.2, 3.3. Now, really quick before we kind of finish this out, Utah also is 3.2, and Wyoming is also 3.2. So we've got 3 3.2s. So there should be 3 2s represented for 3.2. So there's 1, there's 2, there's 3, right? Okay, so I'm sorry, I'm going to have to draw this data on this, but that is how I'm getting this number if you want to kind of follow along with me. I don't have anywhere else to put it. So there's the stem, there's the leaf. Maybe not. Now I'm going to have to redraw it. Sorry. Stem, leaf. So again, we start with 2, 3, 4, 5, 6, 7, 8. And when I did 3, they were not in ascending order, which means we increase. So this data was organized after I got all those numbers, and I did it from smallest to largest. So 2.8, there were 3 3.2s like we saw, 3.3, 3 3.8s, and 2 3.9. So that's where I'm getting these numbers. So 4 4.0s, 1 2 3 4, 6 7 7 8. You want to try to line them up evenly. Like, notice my 2.8, 3.2, and 4.0 are all kind of the same. And I'm trying to do even spacing, although 5's got a lot, so it's going to be hard to fit them all. But that is the goal, because eventually when we learn about shape, you want to distribute it evenly. 1, 2, 3, 4, 5, 4, 5, 5, 5. 7 7 8. Sorry, that's an 8. That's my longest one. Then 6 is 0 2 3 4 4 5 6 8 8 9 9. And then we had one 7.5 and one 8.5. So that's how you do a stem and leaf plot. Now, notice the 5 is really long. That's okay, but I mean, I'll show you a way that we can maybe deal with that if it bothers us, I guess you could say. So because the 5 was so long, we could do something that's called a split stem. And that's when the data appears bunched. We can split it up. The stem and leaf plot shown on the next slide reveals the distribution a little better. And we basically just split it up. It's pretty self-explanatory. So this still represents 2.8, but then we split it up into the upper and lower half of each one, basically. So the first 3 represents 3.0 to 3.4, and the second 3.5 to 3.9. Whenever you do this, you want to make sure that you split them up evenly, and as we know, we only had one 7.5 and one 8.5. So there were no 7.0 to 7.4 values. And if that's the case, you don't put anything. You're not going to put a 0 because that would represent 7.0. So just be careful of that. So advantages of stem and leaf over histograms. Once you put information in a histogram, you lose it, especially with continuous. You know, we had 670 to 679, and then we had 2 values, and it's like, well, what were those 2 values? Were they 670? Were they 671, 672? And so you lose a little bit, but with stem and leaf, we know for a fact that was 2.8, and that was 3.2. And really quick, now that I'm thinking about it, the difference between this and this is very important. This represents 2.8, and that one represents 28. So just be careful. If you need a decimal, use it. If you don't need one, then don't put it. One of the last things we're going to talk about is a dot plot. And a dot plot is drawn by placing each observation horizontally in increasing order and placing the dot above the observation each time. And so I'm going to show you what that looks like in the next slide. So the following data represents the number of available cars in a household based on a random sample of 50 households. Draw a dot plot of the data. So I'm going to write this information again. We had already we did number of cars and the frequency. So we had 4 households with 0, 13 with 1, 22 with 2, 7, 3, 1. Okay, so we did that earlier, but here's what a dot plot is. It is a horizontal line telling us what it is, cars per household, and then our values. So 0, 1, 2, 3, 4, 5. And we're going to draw a dot for each value that we see. So for example, 0 is going to have 4 dots. 1, 2, 3, 4. 1's going to have 13. 2's going to be hard. You want to try to space them evenly, but 2, I'm not going to have enough room, so I'll try my best. There's 22 dots. 3 is going to have 7. 4 is going to have 3. And 5 is going to have 1. So that is a dot plot. It's pretty straightforward. And the next thing that we're going to talk about is shape. But I kind of want you to remember this shape. I'm going to draw a shape around it. Ready? Remember, it kind of looks like a hill. Just remember that as we go move forward. So you've got different types of shapes when it comes to distributions, I guess you could say. You've got something called a uniform distribution. These shapes are drawn on the next slide, but I'm going to draw a little rough shape of them, I guess you could say. So uniform, it looks like this. It looks like a rectangle. It means that the frequency is evenly spread out. So maybe we had 4 values for, maybe we had 4 values for each of whatever we're talking about. And so it ended up making a shape that looked like a rectangle. I'm going to put a U above it for uniform. You've got something called bell-shaped. And it is when the highest frequency occurs in the middle, right? That's the bulk of our data. If think about bar graphs when you're thinking of this. The biggest bar was in the middle. That's called bell-shaped. I'm just going to put bell distribution. It's also called symmetric. Then we've got something called skewed right. And I think of skewed right as it looks like, I'm going to redo that. It says the tail is to the right of the peak. The tail to the right is longer than the tail to the left. And the bulk of your data is to the left. So that's skewed right. I think of that as it looks like your right foot, where your biggest toe is the tallest, and then it goes down. And then skewed left looks like your left foot. The tail's to the left, and the bulk of the data is in the right. So, anyways, that's the 3 types. Here are pictures to support those. They are better than what I could draw, but anyways, if you need shapes to go with these, that's what it looks like. So anytime you're trying to identify a shape, with bar graphs, with histograms, you can kind of make dots in the middle of it and try to connect the dots the best you can. Or you can just make a rough shape, but this looks similar to my left foot. So this is skewed left. The bulk of the data is in the right, and the little tail that they call it, this is the tail, it's to the left. We are not going to do this because we are not in class. We are online. I need to take this slide out of there. Sorry about that. If you want to, you can. But if not, just keep moving on. 2.3 is additional displays of quantitative data. We're going to learn about frequency polygons, cumulative frequency and relative frequency graphs, construct frequency and relative frequency ogives, and time series graphs. So a frequency polygon is just a class midpoint, basically the middle point between the classes that you're looking at. And you find it by adding the lower classes together and dividing them by 2. This is basically finding the average. And then a frequency polygon is a graph that uses points connected by line segments that represent the frequencies for each class. It's constructed by plotting a point above each class midpoint on the horizontal axis at a height equal to the frequency of the class. And then line segments are drawn to connect the 2 points. I think of this as kind of XY, like an ordered pair. And you're going to just plot those points and then connect the dots. It's pretty straightforward. I'll show you how to do it. So we added these together like it told us to. And we got 675, and that's how we got that midpoint. The midpoint basically between all these eruptions. And so that's going to be what I would consider our X value when I say X and Y. And so that's my X value, and the Y is going to be my frequency. And so on the graph that I'm about to show you, that's really how I'm getting these points. So I'm going to draw them over here. 675, 2. 685, 0. And so on, so on. You can kind of think of it like that. So this is what it's going to look like. Sometimes you can start here where your data doesn't even start yet. Like I'm starting at 0, and then this is that 675, 2. 685, 0, 695, 7, so on, so on. You plot all these points, and then you connect the dots. And so it's pretty straightforward. We're using our frequency right now, but you can use the exact same with relative frequency. So as you can see, relative frequency really creates the same graph for the most part, except you're using relative frequency now as that Y value, if you will. But you're still using the midpoints, to give you these values. So a cumulative frequency and cumulative relative frequency distribution is really kind of, I think of the word accumulate. You are accumulating the previous point. So let me read it to you. It says, a cumulative frequency distribution displays the aggregate frequency of the category. So basically, for discrete, it displays the total number of observations less than or equal to the category. And for continuous, it displays the total number of observations less than or equal to the upper class limit of a class. For relative frequency, we display the proportion of observations less than or equal to the category and the proportion of observations less than or equal to the upper class limit. So I'm going to show you on the next slide how we would obtain that information. Okay, so this is the data of the Old Faithful eruption time, and this is basically what we're adding. We're accumulating frequency and relative frequency. And so I'm just going to look at frequency first. So these are the two I'm going to focus on, then I'll go to relative frequency. So you always just take what you're given. So we were given 2, and you add it to the next one, so to get your next value. So I have 2. 2 plus 0 equals 2. Then I take that value and add it to the next one. 2 plus 7 equals 9. So you're accumulating, right? So I'm going to take that value. 9 plus 9 equals 18. 18 plus 9 equals 27. And you just keep going until you get all your points. And we had a total of 45 eruptions. So you should end with the total amount of observations that you had. So we just keep accumulating each one until we get to that last number. Okay, with relative frequency, again, you take what you're given, that 0.044, and you add it. Didn't want that to go away. You add it to the next one. So that plus 0.0444, that gives us that. Take what you're given, add it to the next one, 0.0444, gives us 0.2. Add that to the next one, plus 0.2, 0.4. Take that, add it to the next one, 0.6, and so on until you are at the end. Now, with relative frequency, you should always end up with 1, because that means that you got 100% of your observations, or a whole. Versus cumulative, it just depends on the number of observations that you had. Did you look at 45 eruptions, 50, 20, right? That depends on that number. Okay, this is a weird word. It looks like ogive, but it's pronounced ogive, and it's a graph that represents the cumulative frequency or relative frequency for the class. It's constructed by plotting points, and the x-coordinates are the upper class, and the y-coordinates are the cumulative frequency or relative frequency. Then it's pretty much the same as that frequency polygon, except now it's being done with cumulative information. And so we're going to plot those points and create line segments between the points. So we're going to use the information that we just created with that cumulative frequency. For example, we got 675, 2. And then from 675 to 685 had 0. So remember, it didn't go up any. So with cumulative frequency, it's either going to stay the same if there were 0 observations, or it's going to go up. It's never going to go down, because you're accumulating every time. And you should end, right? We had 45 observations. You should end with the total amount of observations that you had. Same with relative frequency. We're using the data that we created, and you should always end with 1, and you should always either be going straight, right, if there was no growth, or you should be going up. You should never be going down, or you accumulated incorrectly. All right, so time series data and time series plot. Data is the information you're given about that time that you're looking at, and then the plot is what you are actually constructing. So if the value of the variable is measured at different points in time, then that is when we use the time series data. And then the plot, again, is what we use to create that graph. So I'm going to give you all some data. The data says, here's the closing prices of Dow Jones Industrial Average for the years 1990 to 2007. So this is happening over a period of time, which is why we're going to use a time series graph. And similarly to the things that we've been doing, it looks very similar to a frequency polygon and an ogive. In this case, we're going to do the same thing. We're going to have what I would consider X and Y values. So this is going to be 1990, 2,553. Each of these, I didn't want that to go away. Sorry. So for each of these, we have an X value, Y value, X value, Y value, right? We're going to keep going until we plot every single one of these points, and the graph is shown on the next slide. So it can kind of show growth from year to year, right? We just looking at this, I can tell that we pretty much grew all the way up until 1997, and then we were stagnant, and then we grew some more, but from 1999 to 2001, that wasn't a good year. We went down. And so this just helps you kind of, a lot of companies use this to see how they were doing year to year or to compare themselves to other companies. 2.4 is over misrepresentation of data. So we know how to represent data, but now we can learn about ways that maybe data is not presented in a very good way. So this is an example of just when a graph is way too busy. Whenever you create graphs, you want to make it as straightforward and easy to read as possible. And so this is just really hard to read. They've got whatever this risk due to climate change. The color represents something. And then they've got it additionally on some thermometers. And then they've got all these little icons. But then they've got other icons down here. There's just a lot going on here. It's really hard to read. So it's just too many scales to look at. This says the data in the table represents the historical life expectancies of residents of the United States. 2 plots are shown below. Discuss these plots and any misrepresentation. So 95, our life expectancy was basically 68. And 2000, our life expectancy was 77. And so graph A makes it look like we were dying at the age of 0. Right? This is a lot of graphs start at 0. So this looks like in 1990, all the infants were dying. And then it looks like, oh my gosh, in only 50 years, we've come such a long way. So this really kind of makes it look like we have come a long way, right? We've come almost 10 years, but this looks like we've come way longer than we have. So B is definitely your better option. It shows an increase, but not an increase to the extent that it's showing. This looks like it's way too much of an increase. It doesn't do it to scale. So anyways, if you're on Facebook and you see a crazy graph, look at what the data is telling you. Try to see past maybe what you think they're trying to show you. This says a national survey of student engagements, a survey that, among other things, asks first-year students at liberal art colleges how much time they're spent preparing for class. The results are summarized. 2 pie charts are shown on the next slide. So basically, 13% of students studied 1 to 5 hours. 25 studied 6 to 10, so on, so on, so on. And here are 2 pie graphs to represent. So really, a good rule of thumb is 3-dimensional graphs are not good. They're hard to read, and they don't really show you the data very well. I mean, it's just hard to kind of see. So 2D really is the way to go, although it's not as fun for most people. This is definitely better than 3-dimensional. Try to avoid 3-dimensional. So there are a couple guidelines that you really want to stick to. Make sure to always label with a title and the axes clearly. Avoid distortion. Never, ever, ever lie about the data. Minimize the amount of white space. Avoid clutter, like that first one we saw. That was a lot. Avoid 3 dimensions. It's hard to read. It's hard to kind of see what the data is trying to tell you. Don't use more than one design in the same graphic. That's more so if you're using technology, but still. And avoid relative graphs that are devoid of data or scales. Here are some more examples. If you want to go on the slides that I uploaded on Canvas, you can look at a couple more examples.